In this video, we will be talking about the mean value theorem, and we'll use the mean value theorem to do some examples, and then we'll also use the mean value theorem to help us check whether a function is increasing or decreasing at different intervals. So first, we talked about in Calculus AB, we talked about Rawls' theorem, which was a part of the mean value theorem. And so remember, the conditions for the mean value theorem and also Rawls' theorem were that the function had to be continuous on the closed interval, differentiable on the open interval, and for Rawls' theorem, f of a has to equal f of b. And then if those conditions are met, then in the open interval a and b, we know that that function is going to cross the x-axis at some point and has a 0. So for this example, we're going to figure out where this function has a 0 or zeros by just setting f of x equal to 0. So if x squared minus 5x plus 6 equals 0, I can factor that to x minus 2, x minus 3, and we get that somewhere in between 2 and 3, we know that the derivative is equal to 0 somewhere between 2 and 3 there. So we can find c by finding the derivative of f of x, and that's 2x minus 5. We're going to make that c and set that equal to 0. c is 5/2, and we can see that that definitely is between 2 and 3. The mean value theorem then is more overall. Again, we have to have that the function is continuous on the closed interval, differentiable on the open interval, and then what we are saying here is this would be the slope of the secant line over the interval a to b, and we know that the slope of the tangent line at some point in that interval must be equal to the slope of the secant line. That's what the mean value theorem is telling us there. So a lot of the times we use the mean value theorem to approximate what the slope of a tangent is in an interval when we don't have a function and we can't use the derivative to get that. So if we look at this function, we know that it satisfies the conditions because it is continuous on that closed interval of -1 to 1, and it's also differentiable on that open interval of -1 to 1. So we know we can use the mean value theorem. So we find for part B the derivative, which is 3x squared minus 3. And then we can say that if I find f of 1 minus f of -1 over 1 minus -1, that value has to equal this at c, and I can find that number c. So when I plug in 1 into this equation, I get 3. When I plug in -1 into this equation, I get 7. 1 minus a -1 is a 2, so this gives me -4 over 2, or -2. So now I want to say 3c squared minus 3 is equal to -2. So 3c squared is equal to 1. So c squared equals 1/3. So c is positive and -1 over the square root of 3, which we simplify to the square root of 3 over 3. Both of those are in that interval -1 to 1. So those are the places where the tangent line and the secant line have the same slope. So if I were to draw a secant line from the points on that graph at 1, 3, negative 1, 7, if I were to draw a line, that line would have the same slope as the tangent lines at those 2 points, at these 2 points here. That's what that means geometrically. Here we can use the mean value theorem to show that a car must have hit a certain speed. So here we're talking about distance and time. So if we do f of a minus f of b, our distance is 110 and 0. And then our time is, we went 2 hours to go 110 miles, 0 hours to go to 0. This gives us 55 miles per hour. So that shows us that the car had to have that speed at some point in that 0 to 2 hour interval. So these are just some examples about using the corollaries that come from the mean value theorem. Some corollaries about constant functions and specifically velocity. So you can read those through. We can also use then the mean value theorem to determine when a function is increasing and when it's decreasing by finding those critical numbers, using a sign chart, and then figuring out those intervals. Remember that we have to justify that a function is increasing by stating that the derivative is positive. So we have to find where the derivative is positive, and we figure out where a function is decreasing, justify that by saying that is where the derivative is negative. So in this one, the derivative is going to be 6x squared minus 18x plus 12. Factor out the 6. And that factors to x minus 2, x minus 1. So that tells me my critical numbers are going to be 1 and 2. Make my sign chart. Looking at this part right here, since this is always positive, when x is less than 1, both of those pieces are negative and multiplied together makes positive. When x is between 1 and 2, this piece is negative, this piece is positive, so that gives us a negative. And when x is greater than 2, both pieces are positive, which gives us a positive. So in the interval from negative infinity to 1 and 2 to infinity, our function is increasing. And remember, this is because the derivative is greater than 0. And in the interval from 1 to 2, our function is decreasing. And the justification will be our derivative is less than 0. For this problem, we don't want to just look at where the derivative equals 0 for our critical numbers. We also have to look at where the derivative does not exist. So when we get this derivative using the chain rule, we get 2/3 x squared minus 1 to the negative 1/3 power, and then times the derivative of the inside is 2x. Simplifying that, we get 4x on top and 3 times x squared minus 1 to the 1/3 power on the bottom. So our critical numbers are going to be where that fraction equals 0, which happens at x equals 0, and where the bottom equals 0, which happens at x equals negative 1 and x equals 1. Now we're going to use the fraction to determine our sign chart here, determine whether the derivative is positive or negative. So when x is less than negative 1, the top is going to be negative, the bottom is going to be positive, and so we have a negative there. Same between -1 and 0. The top is positive, or is negative, the bottom is positive, so we have another negative. So there's no sign change at -1. It's not an extreme, it's not a max or a min. It's just a place where the derivative does not exist. So it may be a corner, something like that, but there's no sign change, max or min sign change there. When x is between 0 and 1, we get positive on the top, positive on the bottom, and same when x is greater than 1. So when we write the intervals for this one, we want to be sure that we do not say that the function is increasing or decreasing at any of the critical numbers. So we know that it is increasing between 0 and 1 and 1 to infinity. Decreasing between -infinity and -1, and then -1 and 0. And again, if we were asked to justify this, the sign chart is not enough of a justification. We would have to add that the derivative is negative in those intervals and for the decreasing, and positive in the intervals for the increasing. Okay, also we can answer all of these questions using a graph. When we're not given the function, just the graph of a function, and this is actually the graph of the derivative of our function here. So if we want to know what the domain of the derivative is, we want to look at the domain of that particular function. So it's all real numbers except it does not exist at 0, and the derivative does not exist at 2. The critical numbers are going to be where the derivative does not exist and where the derivative is 0. So that happens at x equals -2, x equals 0, x equals 2, and x equals 4. Those are our 4 critical numbers. Again, that does not mean that those are extremes. It just means that those are where the derivative equals 0 or is undefined. We want to know where f has a horizontal tangent line. That can only happen when the derivative is equal to 0. So that happens at x equals -2 and x equals 4. For D, a vertical tangent line is where you have the limit of the derivative is infinity or -infinity, and that happens at x equals 0. For a corner, it's where we have a jump in slope, and that happens at x equals 2. And when we want to know what intervals the function is increasing, that will happen when the derivative is positive, and that happens between -2 and 0, 0 and 2, and 2 to 4. Oops, that was supposed to be for increasing. And finally, for decreasing, we're looking for where the derivative is negative. That happens from -infinity to -2 and 4 to infinity. Okay, and in this word problem here, we are asked to figure out when will the yield increase and when will it decrease. So we again are using the derivative of this equation. So the derivative of this is going to be this part, the derivative is 0, this part is just -0.417, So this part gives us 1/2 of the 0.852, which is 0.426, x to the negative 1/2 power. And then when we get a common denominator for that, we end up with negative 0.417 times the square root of x plus 0.426 all over the square root of x. Putting that into the calculator, what we want to do is we want to figure out where the derivative is positive and where it hits 0. So if we do calc and the 0, we can see the 0 is somewhere around here. So we want to make sure we're crossing the x-axis. And so we see that our 0 happens at 1.044 approximately. The derivative is positive between 0 and 1.44. So that is where the function is increasing. And the function is increasing between that 1.0, or decreasing between that 1.044 and